It's going to be the last lecture of the year. So we're going to talk about chronic responses to altitude. All right, so we've got just the primary responses, and then we're going to talk about live high, train low. So we come back to this wonky figure, and I've still never found a better figure, or at least where the colors match up. So we talked about last time how ventilation, which is here, this green line, increases and then decreases, and then it kind of flat lines, but over time it actually gradually continues to increase. Okay. The other thing I want to kind of point out here is that this gray line, that's capillary density, that gradually increases after about 6 days, and hematocrit starts to increase after about the first day, but really once it gets to 2 to 3 weeks, that's where we see like the maximum change in hematocrit, so the number of red blood cells. And this happens, and I think we'll talk about it later, due to the increased number of red blood cells and also the fact that you lose plasma volume at altitude. Now, when it comes to acclimatization, it takes time, okay? And so there's a lot of research out there to suggest that you actually have to be fairly high, much higher than most people think, before you start to see any real acclimatization effects. So 2,300 meters appears to be kind of the lowest limit before we start to see any real significant effects, and it takes about 2 weeks. And then the higher up you go, the longer it takes. But notice once you get to about 5,800 meters or 19,000 feet, you just don't ever acclimatize because there's such little oxygen there. Now, when it comes to hypoxia, that just means we're not able to deliver enough oxygen to our tissues. And so there can be two components to this. We can have a content component, and then we can have a cardiac output component. So when we're talking about content, we're talking about how much hemoglobin and how saturated the hemoglobin is. When we're talking about delivery or cardiac output, it's heart rate and stroke volume. Now, as we talked about with the respiratory challenges to exercise, we need to protect or maintain alveolar gases. So if you recall, the basic formula is alveolar carbon dioxide equals the amount of carbon dioxide we're producing divided by alveolar ventilation. As we increase alveolar ventilation, all other things being equal, our alveolar CO2 will decrease. And then we've got alveolar oxygen, which takes into account the amount of oxygen we're breathing in, as well as the ratio between oxygen and ventilation. And so the problem that we ultimately face is, well, how can we maintain both of these at altitude? All right, so again, coming back to this equation, we're going to talk about this a lot. We're going to focus on content here. And so content's dependent on hemoglobin and saturation, and so delivery, heart rate, and stroke volume. So we're going to focus on hemoglobin here. All right, so we've got two hematological adaptations. The first, like I said a minute ago, is plasma volume is reduced. And remember, we eliminate or we reduce our plasma volume because we urinate more at altitude because we're in a respiratory alkalosis. And so to compensate for that, we want to urinate and get rid of bicarbonate, which causes us to get our pH back to normal. Okay, so that will increase the concentration of red blood cells, and at the same time, EPO, or erythropoietin, causes us to produce more red blood cells, and then as a result, we're able to carry more oxygen per unit of blood. But it's important to know that in order for this to actually occur and to make a difference, you need to have enough iron. If you don't have enough iron, you can't produce red blood cells, and then you're not able to take advantage of this benefit. I also want to point out that the plasma volume occurs almost immediately, the decreases in plasma volume, whereas the increase in red blood cells takes a couple of weeks. All right, so we can see that actually from this picture here. So initially, and actually let me orient you here. So we have time on the x-axis, change on the y-axis, but the time component is, it's a little unique in that it's 18 weeks between 4,000 and 5,800 meters, 3 to 6 weeks after, while staying at 5,800 meters, and then another 9 to 14 weeks at or above 5,800 meters. So this is almost over the course of an entire year. So notice that we have an initial decrease in plasma volume, which that by itself will increase hemoglobin, but over the first 18 weeks, we also have an increase in red blood cell volume. Okay. Notice that as plasma volume decreases, so does blood volume. And so what happens is we have this big change initially, and then they stay relatively flat. we have this increase blood volume and red blood cell and all that over time, but that's after we're spending, we're 30 weeks in this and we're at higher elevation. All right. So initially plasma volume decreases, which causes a decrease in blood volume, but our hemoglobin concentration and our red blood cell volume increase. And the hemoglobin percentage isn't due just to red blood cell change, but a reduction in plasma volume. So then we can look at we're going to focus on hemoglobin saturation. Okay. And this one we call a free adaptation because we don't have to do anything. It just happens. So at altitude, there's a leftward shift in the oxyhemoglobin dissociation curve, which causes an increase in saturation for a given pressure and oxygen. This is due to our hyperventilation, which decreases the partial pressure of CO2. Now remember, an increase in core temperature or acidity or CO2 shift that curve to the right. Okay. Now what happens, we're going to add an additional variable here, is that when we're at altitude, we actually produce something called 2,3-DP or 2,3-BPG, di or bi, depending on where you're from. Okay, and what this does is this 2,3-DPG actually binds to hemoglobin, which makes it more difficult for oxygen to bind. So at altitude, we increase the amount of 2,3-DPG being produced, and so there's a less attraction between hemoglobin and oxygen. And this produces what we call a Bohr effect. Okay, and so the Bohr effect just basically says if I have a lot of carbon dioxide available or on my hemoglobin, then it's more difficult for oxygen to bind. So we've got this table that summarizes what's going on with the oxyhemoglobin curve and then the time component. So initially when we get to altitude, we experience a respiratory or a ventilatory alkalosis, which ultimately causes a left shift. Don't worry about the up and or the down and. We're just going to focus on the left. So it makes it easier for oxygen to bind. But after being there for several days or weeks, we excrete more bicarbonate. We produce more 2,3-DPG, which causes a rightward shift, which makes it easier for oxygen to unload. Okay, and this isn't as big of a deal because after a few weeks, we have more red blood cells, which means we can hold on to more oxygen. So if it's a little more difficult for oxygen to bind, it's not as big of a deal due to this increased red blood cell volume. And so then finally, let's just focus on cardiac output and regional blood flow. All right, we need to make it easier to get blood into the active tissue. So that's that regional blood flow. And so this happens over time, and this takes a lot of time. So these are similar adaptations that happen to those that happen in the muscle with aerobic training. We're going to have more capillaries, we're going to have more myoglobin, and we're going to have more mitochondria, and they're going to have greater enzyme activity. Okay, and so this allows the muscle to use and get in any oxygen that's available. And so that's an important thing, but this takes a long time just being at altitude. So let's talk about exercise performance. Now, as we said earlier, the time and the amount of acclimatization that a person experiences is dependent on the altitude and how long they're there. Okay, so when you're at altitude, acclimatization doesn't really change your VO2 max at altitude. What it does do, though, is it will help your time to exhaustion, that's what TTE stands for, as well as your time trial performance. But you won't ever have performances as good at altitude as you will at sea level. It's just not possible for a variety of reasons. At sea level, if you become acclimatized to altitude, you're not going to really see any effect to your sea level performance. Okay, and this might be counterintuitive to you because you're thinking about, well, we get all these changes, which is true, but we're getting the changes in the cardiovascular system, but oftentimes we're losing some of the training effects with the muscle. And I'm not just talking about the ability to get oxygen into the muscle. I'm talking about just the stress that we can put on the muscle. Okay, so basically what's happening is we're not able to go as hard at altitude. Therefore, the adaptations are going to be smaller. All right, and so we've got this figure to try and show it here. So we've got two lines here. All right. And so the blue line is your fitness level. The red line is the benefits that you get from altitude. Now, we're going to say here is where we go to altitude. Here's where we end being at altitude. And notice that our fitness goes down, but our altitude benefits, so that increased red blood cell count and hematocrit, that sort of thing increases. Well, you lose your fitness benefits because you're not able to train as hard. And so then when you go back to sea level, your fitness, you're able to improve your fitness, but you're decreasing your altitude benefits because then you start getting rid of these altitude adaptations. Really what it comes down to is this exercise intensity. And so at altitude, you have reduced oxygen availability, which means you can't train as hard. Okay, so if I go to, if I'm up in Park City, Utah, I will not be able to run as fast. I will not be able to train as hard as I will if I'm in Terre Haute, because here we're at like 400 feet to Park City is like 8,000 feet. There's just a lot less oxygen, so I'm not going to be able to train as hard. So as a result, I have decreased fitness. So yes, I'll be gaining, especially if I stayed in Park City for a while, I'll be gaining these altitude benefits, increased blood cells, increased hemoglobin concentration, that sort of thing. But it kind of cancels out. It's canceled out by the fact that I'm not able to train as hard. And so in order to maximize the effects, we need to experience altitude while maintaining training intensity. And I'm not sure where my slide went, but this leads to something called live high, train low. And we're going to talk about this in class, and so I'm just going to give you a brief overview here. Live high, train low, the theory behind it is that if we spend most of our time at altitude, we get all of the altitude benefits. So increased hematocrit, decreased plasma volume, increased red blood cell volume, things like that. But when it comes time to train, we go somewhere that's low intensity. And so that way we're able to stress our muscles to a greater degree, and then we're going to have greater adaptations. All right. And so in order for this to happen, you have to live in a place where you can go live in the mountains, but then go train at like sea level. Okay. And there aren't a lot of places like that. The study that kind of kicked this all off, the high altitude was Park City, Utah, which is about 8,000 feet. But interestingly, the low altitude that they used for that was Salt Lake City, Utah, which is about 4,500 feet. And I know that before I had said this, if I had asked you about it, most of you, if not all of you, would have said Salt Lake City or Denver, mile high or close to it, that would be high altitude. When it comes to physiology, that's not necessarily the case. So anyway, we'll talk about that more in class. But it's been a great semester, so thank you for that, and I will see you on Thursday.